So far, we have looked at how currents respond to magnetic fields and how currents make magnetic fields. Now, we're going to change tack once again and look into how magnetic fields make currents. This process has a few steps, so you may want to watch this video a few times. In earlier videos, we talked about the idea of a magnetic field. We are now going to introduce a new concept called magnetic flux. Here is a magnetic field. Let's say that you take a square sheet of paper and pass it within the magnetic field. Then, some of the field lines would pass through the square. Now, if the square were larger, if it had a larger area, then obviously more field lines would pass through. But on the other hand, if you tilted the sheet of paper, fewer field lines would pass through. We can quantify the angle of orientation by drawing a line that is perpendicular to the plane of the wire. When the sheet of paper is face on to the magnetic field, the line is aligned with the B field. We say that the angle of orientation is 0 degrees when it is face on. When the sheet of paper is edge on to the magnetic field, the line is perpendicular to the B field. We say the angle of orientation is 90 degrees when it is edge on. We're going to use this visualization to provide the definition of magnetic flux. The magnetic flux is symbolized by the uppercase Greek letter phi. Take the strength of the magnetic field, B, multiply it by the area of the paper, A, and then multiply that by the cosine of the angle of orientation. Remember, 0 degrees means face on, 90 degrees means edge on, and tilted would be proportionately in between. Now, we will replace the sheet of paper with a circle of wire. The same calculation applies considering the area to be the area enclosed by the circle. For our purposes, there will be two different ways that the flux through the wire can change. If the wire is far from the magnet and the magnet is brought closer, the field at the position of the wire will get stronger and stronger, so the wire feels an increasing magnetic flux. By contrast, if the magnet is moved away, the magnetic field at the wire would grow weaker and weaker. It would feel a decreasing flux. Also, if the wire is initially face on to the magnetic field and then rotates to edge on, it would feel a decreasing flux. In the equation, that would manifest as an increasing angle. Vice versa, if the wire reorients from edge on to face on, that is 90 degrees to 0 degrees, the flux increases. Strictly speaking, it is possible for the flux to change if the area enclosed by the wire also changes. However, that situation won't come up much in this course. Now that we have an idea of what magnetic flux is and how it changes, the next question is what that change means. The answer is given by Lenz's law. Lenz's law grew out of a very interesting observation. If a loop of wire feels a magnetic flux and the magnetic flux changes, the loop of wire will produce its own magnetic field. To distinguish between the two fields, we will call the field produced by the magnet the primary field and the field produced by the loop of wire the counter field. Now let's be more specific. Here we see the north pole of a magnet approaching the loop. The loop therefore feels a strengthening north pole. The loop responds by creating a counterfield, and look at the orientation of the counterfield. The north pole of the counterfield is left of the loop. In this position, the counterfield north is trying to repel the incoming north pole of the magnet. The loop is trying to repel the incoming magnet. It's opposing the approach of the incoming magnet. Now let's try the opposite. What if the north pole of the magnet recedes? It moves away from the loop. The loop will feel a weakening north pole. Again, the loop creates a counterfield, but in this case, the counterfield is oriented so that the south pole is at the left. The loop has created a counterfield that would attract the magnet back. So to review, when the north pole was approaching, the loop's counterfield tried to prevent it from approaching by placing a north pole right next to it. And when the north pole was receding, the loop's counterfield tried to prevent it from receding by placing a south pole next to it so it would get drawn back. This is Lenz's law. Whenever a loop of wire feels a changing magnetic flux, it creates a counterfield that opposes that change. If the change in magnetic flux was caused by a strengthening north pole, the loop creates a counterfield that repels it. And if the change was caused by a weakening north pole, the loop creates a counterfield that attracts it back. A similar logic holds for south poles, and the same logic holds if the loop rotates. If the loop rotates from face on to edge on, the side that was closest to the north pole effectively feels a weakening north pole, so that its counterfield has a south pole that tries to pull that north pole back. To summarize what we've seen so far, when a loop of wire feels a changing magnetic field, it sets up a counterfield that opposes the original change. But how does the wire create that counter-magnetic field? The same way that wires always create magnetic fields, by having a current flow in them. Remember that a current-carrying wire in the shape of a loop will create this very distinctive magnetic field. How do we figure out the direction of the current? By the second right-hand rule, which we introduced in the video on Ampere's law. If you point your fingers in the direction of the magnetic field, your thumb points in the direction of the current. We can even take this one step further. If there is a current in the wire, there must also be a voltage in the wire. So now we have the full story. The wire feels a changing magnetic flux. It creates a counterfield to oppose that change. But to create the counterfield, it must have a voltage and a current developed within it. Michael Faraday discovered the relationship between the change in magnetic flux and the voltage that develops in the wire. It's given by this equation, the Faraday-Lenz law. The voltage that develops in the wire equals the number of turns in the wire times the change in flux over time. That's Faraday's law. That N stands for the number of loops in the wire, if there are multiple turns. The negative sign just reminds us that the counterfield has to oppose the change in the original field. That's Lenz's contribution. Let's see an example. Here, the north pole of a magnet is shown in red and the south pole in blue. Suppose the external field has a strength of 0.05 teslas. The loop of wire has an area of 0.25 meters squared. It takes 3 seconds to turn from edge on to face on, an angle of 90 degrees. What is the voltage that develops in the wire? And what is the orientation of the counterfield? According to Faraday-Lenz, the voltage depends on the number of turns times the rate of change of flux. Let's expand out the change in flux term. The change in flux is really the final flux minus the initial flux. Since magnetic flux equals field times area times the cosine of the angle between them, we will start substituting that information in. There's only one loop. The B field is 0.05 Tesla, the area is 0.25 meters squared, and the time is 3 seconds. Initially, the loop was edge on, that's an angle of 90 degrees, but it eventually turns to be face on, an angle of 0 degrees. Calculating everything, the voltage is 0.00416 volts. The way the loop is turning, the lower surface of the coil is turning towards the North Pole. It therefore feels a strengthening North Pole. So it would respond by creating a counterfield with the counter North Pole facing the magnet's North Pole. You can use the second right-hand rule to figure out that the direction of the current that yields that counterfield. The current must travel clockwise through this loop for the counterfield to be pointed towards the North Pole. In this video, we were introduced to the Faraday-Lenz law. It says that when a loop of wire feels a changing magnetic field, it creates a counterfield that opposes the change in the external field. To do this, it must develop a voltage and a current. The voltage is given by this equation, and the current must travel in a direction that produces the correct counterfield according to the second right-hand rule.